Hello, welcome to the course on application of spectroscopic methods in molecular structure determination. This is module 20 of this particular course, and in this module we will have a tutorial session on mass spectrometry. Now in the earlier module we posed a couple of questions and we will see if we can arrive at the structures or the answers for those two questions. The first question is given here. A mass spectrum is given here. This corresponds to a compound obtained by evaporation of indole 3-acetaldehyde from a solution in chloroform and ethyl alcohol. In other words, when the evaporation of indole 3-acetaldehyde is carried out from a solution of chloroform and ethyl alcohol, a new compound is obtained, and this mass spectrum corresponds to that particular compound. Now if you observe carefully, the molecular weight of indole 3-acetaldehyde is 159, and that peak is absent in the spectrum, so it cannot be because of the indole 3-acetaldehyde. The molecular weight is 333 for this compound, as it is mentioned here as M plus ion, and this is about 74 mass units more than the starting material. Suppose if the indole 3-acetaldehyde had reacted with chloroform, then it must contain some chlorinated compound. Such is not the case because the chlorine isotopes are not seen in the molecular ion region. If it had been a reaction with the chloroform, chlorinated product would have been formed, and as a result chlorine containing product would have been formed. As a result of that, M plus and M plus 2 ions would have been seen in the mass spectrum. Therefore, the obvious choice is that the indole 3-acetaldehyde has reacted with ethyl alcohol. Aldehydes react with alcohol to give acetal as the product. So the most likely reaction is indole 3-acetaldehyde is reacted with ethyl alcohol to give the diethyl acetal of indole 3-acetaldehyde. Now the molecular weight of this compound corresponds to 233. It matches with the molecular weight of the substance that is shown in the mass spectrum of this compound. So let us see if the fragmentation pattern of this compound also matches with the peaks that are seen in the mass spectrum. Now a diethyl acetal of this type can undergo fragmentation of this carbon-carbon bond, because that will result in a stable carbonium ion, either this one or a stable carbonium ion which is this one, because this is stabilized, resonance stabilized by oxygen lone pair participation in the delocalization process. So either of the fragment can form with the corresponding positive charge on it, and the molecular weight of the fragment are 130 and 103 respectively for these two fragments. Alternatively, this carbon-oxygen bond can be cleaved. That will also give an oxonium ion, which is relatively a stable species with the loss of 45 mass units corresponding to OET minus the loss of OET, for example, in this particular case, and the oxonium ion has a M by Z value of 188. Whenever an oxonium ion is formed, it is followed by a onium ion reaction. Onium ion reaction is essentially the migration of a hydrogen from the beta position to the onium atom, that is in this particular case the oxonium oxygen atom, with the concomitant loss of a molecule of ethylene in this particular case. So loss of 28 mass unit will give you a fragment which corresponds to 160. So the migration of the red hydrogen onto the oxygen followed by cleavage of the carbon-oxygen bond results in the protonated species of the indole 3-carboxaldehyde, and the loss of 28 mass unit is accounted by the loss from 188 to 160. Now let us see if the mass spectrum of this particular compound has these fragments, namely 188, 130, 103 and 160. It does indeed have the peaks corresponding to 188, 160, 130 and 103. 103 seems to be a very intense peak, and relatively speaking the other peaks are also not too bad in terms of the intensity, except for the 160 peak. Now let us try to identify what is the peak corresponding to 47 and 75 in the fragmentation pattern. This oxonium ion has two ethyl groups with beta hydrogen, so it can another fragmentation process can take place, namely the onium ion reaction can take place by the migration of the beta hydrogen onto the oxygen, giving the protonated form of ethyl formate, which has a molecular weight of 75. This can further undergo hydrogen transfer from the beta position to the oxygen, resulting in the formation of the protonated species of formic acid, which is 47 mass units. So those peaks are also seen. 47 mass unit peak is the base peak peak in this particular spectrum. So the structure of this molecule in terms of its molecular weight as well as the fragmentation pattern has been accounted for by the mass spectrum that is shown in the picture in this particular problem. Let us move on to the next problem. The next problem deals with an element which is in the form of a cluster. In other words, if you look at the mass spectrum carefully, there are many peaks, but if you consider the adjacent peaks, each one of the adjacent peak corresponds to a mass unit difference of 32. So 32 plus 32 is 64, 64 plus 32 is 96, plus 34 is 128, plus 34 is 160, and so on, all the way up to 256. So 8 times 32 is 256, and an element with an atomic weight of 32 would be sulfur. So we are talking about the sulfur S8 cluster. Sulfur S8 is supposed to have a crown structure like this with a molecular weight of 256. With the loss of sulfur atoms one after the other, it will result in the formation of the monoatomic sulfur cation radical at m by z 32. All the intermediate stages mass correspond to the various peaks that are seen in this particular spectrum. The fragmentation actually need not be sequential as it is shown in this particular mechanistic scheme. Two bonds can break at any point of time in this molecule, resulting in the S3, S4 or S5, S6 fragments from the S8 fragment directly. So as a result of that, the following fragmented ions can be formed either sequentially or non-sequentially in a particular manner to account for the various peaks that are seen in this particular spectrum. Mass spectrometry is a very powerful tool to identify substitution pattern, particularly if the substitution is because of a higher isotope of that element. Let us consider this reaction. Here the deuterium is substituting the hydrogens in benzene all the way up to benzene D6 as the molecule. The most convenient way to follow this particular reaction is using mass spectrometry, because with the incorporation of every deuterium, the mass of the resulting molecule changes from the parent molecule. So benzene has a molecular weight of 78. So if you look at the benzene mass spectrum, it will have a base peak at m by z value 78. Upon substitution of a deuterium by heating it with the DCl and D2SO4, both of them are diluted with D2O, for example. The hydrogens can be substituted sequentially by deuterium. So the monodeuterO compound has a molecular weight of 79. So the mass spectrum of, once the monodeuteration is complete, the spectrum would correspond to 79 m by z value of the base peak of the molecular ion. Now the reaction can proceed further, and during the course of the reaction, if the aliquot amount of samples can be analyzed by a GC mass spec, it will clearly reveal whether it has gone to monosubstitution, disubstitution, or trisubstitution, or complete substitution to benzene D6. When it goes all the way to benzene D6, the m by z value corresponds to 84, 6 mass units more than the molecular weight of benzene itself, for example. So there is mass spectrometry is a very convenient way to follow such reaction where the isotope substitution reactions are carried out. This is further illustrated in the next example. Suppose if you take toluene and do the reaction and stop the reaction at the tri-substituted stage, one can have either this product or this product. This is a product where the aromatic ring protons have been substituted by deuterium at specific positions of ortho and para position with relative to the methyl, or the three hydrogens of the methyl themselves are substituted by deuterium to give a CD3 compound. How do we identify whether the particular reaction has given substitution on the aromatic ring or substitution of the side chain in this particular reaction? Now if you look at the molecular weight of this compound and this compound, which contains 3 deuterium, this is 3 mass units more than toluene, but they cannot be identified, they cannot be distinguished purely based on their m by z value, because both of them have 95 m by z value because the molecular weights are same. However, if you look at the fragmentation pattern, the most prominent fragmentation pattern of toluene is loss of hydrogen from the side chain to give the benzyl cation, which is mass spec m by z value 91, which rearranges to the tropylium cation eventually. If such a reaction were to be facile with toluene, it should also be facile with deuterated toluene. This is a tri-deuterated toluene. This is also a tri-deuterated toluene. In this particular case, this can lose only a hydrogen atom to give the tri-substituted benzyl cation with the m by z value of 94. whereas this particular molecule with the CD3 would lose a deuterium to give 1 mass unit lower. In other words, this is a benzyl cation with a CD2 unit present in the system. So one can easily now distinguish based on the mass spec of the benzyl cation. If it is toluene, unreacted substrate, if it is there, it will give 91. If it is a nuclear substituted derivative, in other words, the aromatic ring substituted derivative, it will give a base peak around 94 in the mass spectrum. Or if it gives a spectrum at 93 m by Z value, then it would indicate that CD3 is actually the compound that is formed. In reality, when you do the reaction, it is actually the ring hydrogens are substituted by deuterium to give the trideuterotoluene, because the identification of m by Z value 94 would correspond to only this particular peak, and this would be 93 and this would be 91. So mass spectrum is a very valuable tool even when you do substitution reaction, particularly when the substitution is a higher isotope of a given element, for example. This is further illustrated in the oxygen labeling of this particular ester. This is phenylacetic acid. Phenylacetic acid can be converted into the corresponding acid chloride. When the acid chloride gets hydrolyzed by water O18, there are two acids that are formed because of the rapid proton exchange that can take place between these two oxygen. The oxygen that is originally present in the molecule is O16, and the oxygen that enters from the water molecule is O18. So one can have either the carbonyl oxygen as O18 or the OH oxygen as O18. In fact, you will get a 1:1 mixture of these two compounds when this reaction is carried out. On the other hand, if methanol OA18 is used for quenching the acid chloride, then one gets specifically the OCH3, where the oxygen is 18 labeled oxygen. That would be the only product that is formed here. Now the mixture of these two acids can be converted into the acid chloride, which will give these two mixture of acid chloride with OA18 label and without OA18 label. Subsequently, when it reacts with methyl alcohol, for example, it will form two esters. One ester devoid of any oxygen 18 isotope, another ester where the carbonyl oxygen is labeled with an oxygen 18 isotope. So one can easily distinguish the formation of the differentially labeled. In this particular case, the labeling is on the carbonyl oxygen, whereas in this particular case, the labeling is on the OCH3 of the ester. How do we differentiate this labeling? By simply looking at the fragmentation pattern. The most prominent fragmentation of this particular molecule would correspond to the loss of methoxy radical to give a oxonium ion or the acyl cation of this type with the m by Z value of 119 with the loss of the oxygen 18 isotope of the molecule during the fragmentation process. On the other hand, if mixture of these two esters are present in the system, in other words, if the reaction has proceeded in this manner and the labeling has left in the carbonyl oxygen compound, then the fragmentation pattern will have both 119 as well as 121. In this reaction, the 119 will be the sole fragmentation process, whereas in this case, since this is a mixture of two compounds, both 119 and 121 will be formed, indicating the oxygen of the carbonyl is the one that is labeled in this particular system, whereas the oxygen of the OCH3 is what is labeled in this particular reaction. So this illustrates essentially the utilization of mass spectrometry for the identification of isotopically labeled substrate very effectively, because the masses are different and mass spectrometry works on the basis of the masses of the molecule. Now let us try to analyze this particular spectrum. The spectrum corresponds to para-amino ethyl benzoate. Para-amino ethyl benzoate is a painkiller, and this mass spectrum corresponds to the electron impact ionization mass spectrum of this particular compound. The molecular formula is given C9H11N2, and the structure of the compound is also given here. If you look at the mass spectrum, the fragmentation corresponds to the loss of 45 to give a mass at 120, and the loss of 28 corresponding to a mass at 137. The ester of this type, in other words, the ethyl ester, always gives a peak with the loss of 28 mass unit because of the McLafferty rearrangement. This is alpha, the oxygen is alpha, this is beta, and this is gamma carbon. The gamma hydrogen, which is the methyl hydrogen, can be transferred onto the oxygen with the loss of ethylene unit, which is a 28 mass unit loss corresponding to a fragment at 137, which would be para-aminobenzoic acid in this particular case. Para-aminobenzoic acid, this molecule can also lose a ethoxy radical to directly give a loss of 45 mass units to give the 120. The fragmentation pattern can be seen here. From the molecular ion, a McLafferty rearrangement gives the 137 fragment, which is this particular fragment, namely para-aminobenzoic acid. From the para-aminobenzoic acid, one can lose the OH dot to give the acyl cation, which is at 128, or directly from the molecular ion, it can lose a ethoxy radical to give the same acyl cation in this particular case. This loses a molecule of carbon monoxide with a loss of 28 mass unit from 120, resulting in the formation of a fragment at 92, which probably corresponds to this particular structure, similar to a tropylium ion structure, for example, except it is substituted with one nitrogen because of the nitrogen present in the para position. So the fragmentation pattern essentially is consistent with the structure, or the mass spectrum is consistent with the fragmentation pattern that we have seen. And the important message is that ethyl esters always give a McLafferty rearrangement with a loss of 28 mass unit from the parent molecular ion to give a fragment ion, which is 28 mass units less than the molecular ion peak. Here is an interesting mass spectrum. This is a hydrocarbon molecule with a molecular weight of 180. So one actually sees the molecular ion peak, fairly intense peak is seen in this particular case. And the second fragment that is seen, which is a base peak, is 165, corresponding to 15 mass unit loss in this particular case. The 15 mass unit can only be a cleavage of this carbon-carbon bond with the loss of the methyl group, resulting in diphenyl methyl cation, which is a resonance stabilized stable cation. You don't see any further fragmentation because of the relatively high stability of the diphenyl methyl cation, which is recorded as the base peak in this particular case. Interestingly, the mass spectrum also shows some impurity peaks, essentially coming from the atmospheric nitrogen and oxygen. There is a peak, if you observe carefully, at 28 m by Z value and 32 m by Z value. Most likely these peaks are coming from the contamination from the atmospheric nitrogen and oxygen, corresponding to 28 molecular weight and 32 molecular weight respectively for these two elements. Now let us consider the mass spectrum of this particular ester. This is the phenylacetic acid phenolate ester is what is formed here. The molecular weight is 226. What is important to observe in this particular molecules fragmentation is there are two fragments formed, which is roughly half of the 226. In other words, 108 and 118 are the two fragments that are formed. If you add 108 and 118, it corresponds to 226. In other words, the molecule fragments and the charge resides on both the fragments corresponding to 118 and 108 in this particular case. Let us see the fragmentation process. The fragmentation process is essentially migration of this beta hydrogen. This is alpha carbon. With respect to this oxygen, it is alpha and beta. Hydrogen migration to the oxygen, resulting in the formation of paramethyl phenol, in other words, paracrysol at molecular weight of 180, m by Z 108 in this particular case. And simultaneously, it also gives the phenyl ketene as the product with the molecular weight m by Z value of 118. In other words, this particular molecule fragments such that the two fragments, either of them can have a cationic charge in the resulting structure. For example, if you add up these two numbers, that corresponds to 226. A simple fragmentation of the acyl carbon bond can result in the benzylic cation, which is rearranges to a tropylium cation with a molecular weight of 91, and the 91 peak is also shown in this particular spectrum. Again, you see a peak at 28, probably corresponding to carbon monoxide that may be coming from this particular fragment, for example, resulting in the formation of the CO is seen in the mass spectrum as a peak around 28. So the fragmentation essentially corresponds to a hydrogen migration with the concomitant breaking of the carbonyl carbon bond in this particular molecule, for example, resulting in the formation of these two fragments, which account for the overall fragmentation of this particular molecule. Here is an interesting aliphatic compound. This aliphatic compound undergoes fragmentation quite extensively because the molecular ion peak is a very weak peak in this particular case. The molecular weight is 119. It is an odd molecular weight because it is a nitrogen containing molecule. The difference between 88 and 119 is 31 mass units. So one has to account for 31 mass unit. If you break this particular bond and look at the resulting fragment CH2OH, for example, loss of CH2OH will be a fragment corresponding to loss of 31 mass unit. In other words, this breaking of this particular bond essentially from the cation radical results in the formation of an iminium cation. That iminium cation has a molecular weight of 88 and the structure corresponding to the iminium cation is this particular iminium cation. It's quite possible that the iminium cation actually exists in a cyclic form because this is 1, 2, 3, 4, 5. It can form a 5-membered ring, for example. And as a result of that, this could be a stable ion to give a peak which is fairly intense peak in terms of the relative abundance. On the other hand, further fragmentation by a hydrogen migration to the amine followed by loss of vinyl alcohol result in the formation of a loss of 44 mass unit which corresponds to the vinyl alcohol, resulting in the formation of this particular iminium ion at 44 mass unit. So the 44 mass unit, this is exactly half of the molecular weight of 88 giving 44 with the loss of vinyl alcohol as a fragment in this particular case. So essentially all the major peaks in the compound fragmentation process has been accounted by the simple fragmentation process in this particular molecule. Finally, let us consider an interesting example of a polyhalogenated compound. This is tetrachloroethylene is the molecule. Tetrachloroethylene has 4 chlorine atoms. Therefore, it must have the following molecular ion cluster peak is what is to be seen. All the chlorine atom being 35, the molecular weight will be 164. If one of the chlorine atom is 37 and the rest are 35, then it will be 166. Then 2 of them are 37, for example, would give 168. 3 of them as 37 would give 170. All 4 of them are 37 would give 171. Indeed, one sees the cluster of peaks in the molecular ion region for this particular compound. This is a positive ion mass spectrum is what is shown here in this particular spectrum. And the molecular ion region, one can see 164, 166, 168, 170. The 172 peak is probably too small to be seen relative to the base peak, which is 100. This is only 1%, whereas the 166 peak is the 100 base peak in this particular spectrum. One can also see the relative intensity to be essentially following the trend that is shown here. This is calculated based on the expected line intensities of this, based on the natural abundance of the 37 and 35 isotopes of chlorine in nature, for example. And 164 is about 75% and the base peak is 166 as predicted by the calculated values of the relative abundance of these peaks. What you see subsequently is the loss of one chlorine mass unit corresponding to this cluster of peaks, another chlorine mass unit corresponding to this cluster of peak, and finally another chlorine mass unit loss corresponding to a chlorine cation radical itself is seen here. 35 and 37 are seen very clearly. The peaks at 47 and 82 essentially corresponds to dichlorocarbene cation radical, which is 82 mass units, or CCl fragment corresponds to 47 mass unit. So essentially the entire range of peaks that are seen in the mass spectrum of this compound can be clearly accounted for by the fragmentation, by the sequential loss of chlorines from this molecule, as well as the fragmentation corresponding to the breaking of the carbon-carbon bond, resulting in the formation of CCl2 and CCl as fragments which account for all the masses in this spectrum. Now what we have seen in this module is sort of a tutorial session trying to solve some problems based on the mass spectrum. Most important thing is that we have demonstrated how isotope substitution reaction can be conveniently studied by mass spectrum. We have 3 examples of isotope substitution. First 2 examples are deuterium substitution on toluene and benzene, and the second example is oxygen 18 substitution in an esterification reaction. Thank you very much for your attention.